linear algebra past this one is basically just that, just linear systems of equations. It's not true exactly, but it's that's what it's based on. So yeah, let's talk about what a system of equations is. Let me whip up a whiteboard here. So a system of equations is just two equations, or two or more equations that are all true at the same time. So for instance, you could have an equation like y equals 2x minus 1, and then another one where you have y equals 1 minus 5x. Let's do 1 plus 5x. So that's two equations, and if it is a system of equations, we are looking for which x and y values would make these true at the same time. So in general, this is sort of a basic rule that won't really come up for us very much, but just in general, you can find a solution to these if you have the same number of variables as you do equations. Here we have two variables, x and y, and two equations, obviously these two. So we could find a solution to this, potentially. There are a couple of exceptions, and so I want to start by talking about there's basically only three situations that you can be in if you only have two variables and two equations, which is all we're going to be dealing with. This gets significantly more complicated when you add more variables and more equations, but we're not going to worry about that. We're just doing, it's called a 2x2 system, two variables, two equations. So here's the idea. I'm not going to use these equations just yet. What I want to do is sort of give you a general picture of all the situations that you can find yourself in when you're doing a system of two equations, two variables. Turns out there's exactly three, and there really aren't any more. We're kind of ran out of room there. That's okay. So you could have the base case, the usual case where you have a line, there's one of your lines, and then another line. And they cross in a point. That is by far the most common case, but not the only one. There are two more. One of them is if you have a line and another line that is parallel to it. And I'll talk about why these are the only three cases possible in just a second. And the third case is if you have a line, and I'm not going to be able to draw this very well, but you have a line and then another line that is secretly the same line and is lying right on top of it. So I'm going to draw this next to it, but just know that this is supposed to be the same line. It's not next to it, it's actually right on top of it. So your usual case here, your two blue lines case, this is called consistent and independent. And I'm not going to use these words very much. You know what? In fact, I'm not even going to worry about them for right now. The thing I want to talk about is what a solution looks like to a system of equations. So let me go back here for a second. This is two lines, right? If you think back to when we were just starting to graph lines, and I talked about what it means to be a graph. Graph is all the solutions to an equation, right? So if I could graph this line, y equals 2x minus 1, might as well do that real quick, because we know how that goes, right? 2x minus 1 has a y-intercept of -1 and a slope of 2. So it looks something like this, right? There's y equals 2x minus 1. And every single point on this graph is a solution to this equation. Well, if I graphed y equals 1 plus 5x, right? So has a y-intercept of 1 and a slope of 5, so it's steeper. Every single point on that graph is a solution to this equation. So if I'm looking for all the points that are solutions to both of them, what I want is the points that are on both graphs. Well, there's only one of those. It's the intersection, right here. That is where both of these equations, that's the x and y value that works in both equations because that's the only point on both of them. And this brings up why there are exactly 3 cases. Case 1, you have a solution right here, right? That's where they cross. That's the solution. Case 2, you have no solutions because they don't cross, right? We're looking for some point that's on both lines, and there aren't any because they don't touch. And in case 3, we're looking for some point on both lines, and it's all of them, right? Every point that's on one line is on the other line because it's actually the same equation. And you might say to yourself, well, that's ridiculous. I would see that immediately. It's actually a little subtler than you might think, but with a little bit of work, it does become pretty obvious. And there's actually not any other way to arrange 2 lines on a plane. They either have to cross, never touch, or be the same line. There are no other options. So that means that in this case, there's exactly 1 solution. In this case, there are no solutions. And in this case, there are an infinite number of solutions. So let me write that. So we're going to have 1 solution. And it's right here. And this is by far the most common case. You have to, I don't want to say get tricky, but you have to get a really special case to have either of the other ones. And we'll describe what that looks like. So no solutions. And then the last one is infinite solutions. Infinite solutions. That doesn't mean that literally every point is a solution, but it does mean that every point on the line, on either one of the lines, so they're the same line, is a solution. And there's an infinite number of those, obviously. So let's see what this looks like. Now, we're going to learn how to actually solve this algebraically in the next topic. For right now, I basically just want you to be familiar with these, or familiar with the basic ideas. So essentially, what we're going to be doing in order to handle this topic is we're just going to graph the lines, see about where they cross. That's going to be our estimate of the solution, which is actually not a great way to do the solving. But it's like a quick and dirty way to get a reasonable guess as to what the solution might be. But what I really want you to do is be able to graph the lines, identify the number of solutions based on the graph, and then have a reasonable estimate of what that solution might be if it exists. And that's really all I want you guys to do. So the thing I want to point out before I do any examples is the following. The real defining characteristic of which situation you're in is the slope of the lines. If the slopes are the same, then the lines are either parallel, that is to say they never touch, or they are the same line, which is to say they always touch, right? There's no way you can have 2 lines with the same slope that do this. To cross just once, you have to have lines with different slopes. And that's the defining characteristic. If the slopes are the same, you're in one of these weirdo cases. And if the slopes are different, you have the simple case where you just have 1 solution. If the slopes are the same, the other thing to check is any point on the line, which is usually the y-intercept. Usually look at the y-intercept and see if the y-intercepts are the same and the slopes are the same, well, that's clearly the same line. If the slopes are the same and the y-intercepts are different, then you have different lines. And if they're different, you have no solutions. Same, you have infinite solutions. So let's see a couple of those. Now, these systems of equations, for reasons that you will see when we start doing algebra with them, are usually presented in standard form, the form ax plus by equals c. That's by far the most common form to represent systems of equations in, which I know it's not good for graphing, but it is actually good for the algebra that we're going to do in the next section, or next topic, I should say. So if I have 2 lines, let's say I've got 3x minus 5y equals 11 and 2x plus y equals -7. All right, so let's say I have those 2 equations. both lines, both presented in standard form. And all I'm looking to do is figure out how many solutions there are. I can tell without doing any work that there's one solution, because I'll go through this. So we're going to find the slope of both of these lines, and we're going to see that it's different. And I'll show you how you can tell that it's different without doing any work, right? To identify the number of solutions. Now, I have no idea what the solution to this system is. It's probably some terrible fraction, and I'm not even going to worry about it. All I'm going to do right now is graph the lines and get an estimate and identify how many solutions there are. So the way I'm going to graph the lines, I'm going to turn these both into slope-intercept form, right? So we'll do it, I don't want to say kind of fast. We'll just do it. So we've got 3x minus 5y equals 11. I will subtract the 3x over. And then I will divide by -5. All right, let's do the other one. I will subtract the 2x over. And then I'm done. And the thing that I noticed here is this slope and this slope are different. So that means that we will definitely be in this situation. Either of these weirdo situations requires that the slopes are the same, and they are not the same here, so definitely one solution. Now we'll go ahead and graph these. 3/5 x minus 11/5. We're going to need a new page for this. So we have y equals 3/5 x minus 11 over 5. And y equals, was it 2x minus 7? Minus 2x minus 7. Minus 2x minus 7. All right, so we'll go ahead and get our graphs going, our graph going. Not exactly evenly spaced, but it'll be fine. So the first one, 3/5 x minus 11/5. So my y-intercept is going to be 0, negative 11 over 5. Now 11 over 5 is 2 and a fifth. 5 goes into 11 twice, has 1 left over. So I'm going to go a little bit less than -2. So something in this region. And we're going to have a slope of 3/5. So I want to go up 3 and right 5. So we've got -2 and a fifth here. I'm going to go up 3. So 1, 2, 3, just below this one here. And right 5. So 2, 4, 5. So here. Probably shouldn't have actually drawn in that first one, but it's fine. There's the first line. And the second one, y equals -2x minus 7. So we're going to go down to -7 on the y-axis. 2, 4, 6, that's the bottom one. Okay. And then we are going to have a slope of -2. So I will want to go 1 right and 2 down, or alternatively, I could go, so we can go 1 right and 2 down, right, and be here. Or alternatively, I could think of it as going 1 left and 2 up, right, because that's still the same line. Something like that. I'm not at all worried about precision here, because this is not like graphing and then estimating a solution from that is not at all precise. Like don't think that you're going to get a good solution doing that. We're in this general vicinity though, right? Around -2 in the x and -3 in the y, something around there. That's almost certainly not the exact solution, but in that general vicinity is what I'm looking for. And notice they cross just like we knew they would, because they have different slopes. Now, here's how I could tell before we did any work at all that these had different slopes. Look at how we found the slope. What we did was we moved the x over, removed the x term over here, and then divided by the y term. So the slope ended up being the coefficient of x over the coefficient of y. or negative coefficient of x, right? Because when we moved it over here. So what I was really looking for was the ratio of the coefficients on x and y, right? Here they're 3/5 or negative 3/5, but since we move the x over, the sign switches. Right, so 3/5, and then this one was 2, which is a different number. So I knew that they would be different. And that's all I was doing when I made this problem up literally a couple minutes ago. That's all I did to ensure that they would have different slopes, is I just made the ratios here of the coefficients different. And so if you see something presented in standard form and has the ratios of the coefficients being different, then it's not the same slope and you've got one solution. Right? Anytime the slopes are different, you end up in the one solution case. If the slopes are the same, then you have to find the intercepts and see if they're the same or not. And that's it. So we were in the general vicinity of -2, -3, but obviously my lines are not perfect, and this is not like the exact solution. I just know approximately like the neighborhood of where the solution is. And I'm not relying on my graph to be like precise or perfect. So let's do another one. Let's look at one of the other situations. Now, I'll show you what I'm going to do for this. I'm going to make the ratios of the coefficients the same. I'm going to be super subtle about it, having told you now. So if I do like 2x minus 3y equals 6, and let's say minus 4x plus 6y equals 12. And I'm going to make that -12, actually. There we go. Those don't, at first glance, necessarily look like the same line. But if I do x over y, or the coefficient of x over the coefficient of y, and make it negative, right, I get 2 over 3, and it's already negative 2 over -3, and change the sign, I get 2/3. And if I do -4 over 6 and change the sign, I get 2/3. So these guys are going to have the same slope. Now I'll go ahead and solve just so you can see that. But that's the thing that I'm looking for, is what's the ratio of the coefficients of x and y. So let's go ahead and do that. So do the first one, 2x minus 3y equals 6. Subtract 2x, I get minus 3y equals minus 2x plus 6. Divide by -3, I get y equals 2/3, x minus 2. Same thing for the other one, minus 4x plus 6y equals -12. Add 4x to both sides, 6y equals 4x minus 12. Divide by 6, y equals 4 over 6, and I'm going to reduce these in a second, x minus 12 over 6, which is 2, and then 4/6, of course, is 2/3. Y equals 2/3 x minus 2. So you might notice that these guys are the same. They're the same equation, right? So this is that third situation where the two lines are secretly the same line, even though they don't necessarily look like it from the beginning, right? It's not, if you just glanced at these and didn't really think about it too hard, it would not be clear that these were the same line at all. They are. And the way you can tell is by looking at the slope-intercept form. So I'll go ahead and graph these, right? 2x minus 3y equals 6 and minus 4x plus 6y equals -12 are actually the same line. So I really only have one thing to graph, but I'll go ahead and do that, right? Just do it here. Run it a little low on space, but that's fine. I have a y-intercept of -2 and a slope of 2/3. So I'm going to go up 2 and right 3. And that is both of the lines, right? So if I graph the other one, it would clearly lay right on top of the first one because it's the same line. So this, we would say that this has that this system of equations here has an infinite number of solutions, right? Any point on this line is going to be a solution to both because they're the same line. So let's see what the third case looks like. So I'm going to use something really similar here. I'll do 2x minus 3y equals 6.
minus 4x plus 6y equals 10.
And now in this case, what we're going to see, notice that I kept the same coefficients on the x's and y's on purpose, so you would recognize that the ratio is the same. But this time I changed what these are. All right, the only one I changed was this one. But I'll go ahead and do the same thing we just did a second ago. And I'll do it a little fast since you saw me do it before. So 2x minus 3y equals 6 minus 2x. I guess I'm going to do about the same speed. Equals minus 2x plus 6 divided by negative 3. Y is 2/3 x minus 2. And that moved my whole screen, pardon me. That's what I get for drawing on my screen here. We got minus 4x plus 6y equals 10. Same thing as before, 6y equals 4x plus 10. Divided by 6, y equals 2/3 x plus 10 over 6 this time, which is 5/3 when I reduce it. And now notice that these two are not the same line, right? They're not the same. They do have the same slope, right? The slope of the line is 2/3 in both cases, which means, if you remember what same slope means, that they are going to be parallel, right? They're going to be parallel like this, where they don't intersect at any point, and then therefore there are no solutions. But let's see what it looks like when we graph them. So 2/3 x minus 2, 1, 2, 1, 2, 3. So it was like this. And the other one, 2/3 x plus 5/3. Well, 5/3 is 1 2/3. 1 2/3 is a little bit less than 2, so here-ish. And it's got a slope of 2/3, so it's parallel to this other line. So I'm going to go up 2 and write 3 and get something that looks roughly like this. It's not my best drawing of parallel, but I hope it's clear. And so we can see that they will never meet because they don't go through any of the points that are the same, and they're going the same direction. So they're just going to keep going in that same direction without ever touching. So there are no solutions to this question or to this system of equations. And notice that the no solutions and infinite solutions are actually quite similar, right? No solutions and infinite solutions both have the same like x and y ratio here. The only difference is the thing you get is that the y-intercepts here just do match if you have an infinite number of solutions and don't match if you have no solutions. And then the normal case, the one that's by far the most common, is this, something like this, where you just have two lines and they touch on a point, just like most lines do. And this happens when they don't have the same slope. And that's it. That's all I'm really looking for you to know about solution of, I'm going to say solution by graphing. It's not really a solution, right? It's just getting an idea of how many solutions there are, maybe estimating it if there is one. But I really want you to more think about the situations that you could be in, which is these three that we've described. And that's it. That's really all I really want to say about this. So I'll go ahead and end this video now. Maybe we finally have a short one, and I will see you guys in the next one.